Okay, thanks for being here today, guys. We got a really interesting talk, and I've kind of been excited to get this one all year, talking about LES and DNS simulations on GPUs. And I'm going to be speaking to questions that come up all the time with respect to understanding how to use M-Star, understanding what LES is, how it relates to DNS, what energy dissipation rates mean, how resolutions inform simulation outputs, particularly in terms of turbulence resolution. And so this is going to be an interesting one today. It's not terribly heady. As in some of our previous ones, unlike effective heat transfer, it's going to be a bit more applied, but it will require a little bit of understanding about some of these turbulence phenomena as we discuss them today. So roadmap, motivation approaches studying turbulence. Why we're interested in this as process engineers, and some of kind of the general principles and waypoints we'll consider as we march through this discussion. We'll talk about the relevant length scales. These to us include the integral, Taylor, and Kolmogorov length scales. And now we can use these to characterize turbulence in a universal manner in terms of non-dimensionalizing the length scales and time scales of turbulence according to these intrinsic time scales. We'll talk about LES versus DNS, the gives and gets of both, the expenses associated with DNS, as well as the conditions required to have an LES simulation convert to or begin to recover DNS results. I'll talk a bit about implicit large eddy simulation as well as speed. ILES is interesting because it requires no explicit turbulence modeling. It's a higher order kernel that doesn't modify the viscosity. It has some compelling, attractive features. It's built in M-Star and worth using, as we'll see. So why do we care about turbulence? Because as process engineers, it governs almost everything, right? Whether we're talking about blending time scales, KLA, bubble breakup, whether we're talking about reaction kinetics, the competition between fast and slow kinetics. Here's an illustration taken from Keck, just of like 3 different impeller speeds operating the same vessel, illustrating a few things. They call good, better, best. They're just these conceptual tags down here at 1, 2, and 4 times the impeller speed. They're just characterizing blending here. But what's interesting here is, yes, the faster impeller speed blends faster. What's kind of cool here is the self-similarity of the systems, in that the 8 times faster blend time, it's cool and all it's happening because the impeller speed is spinning 8 times faster than the good, as it were, but it's the same physics, as it were, in terms of the macroscopic integral scale, evolving just 8 times faster. I always get impressed with this self-similarity of turbulence, that if you didn't know the time scale or frame rate, as it were, you wouldn't know what just looking at the integral scale, what the impeller Reynolds number must have been. So in terms of blending, this has a self-similar behavior. In terms of human organic timescale, there may be a difference. If there's some other, say, reaction kinetic timescale, then this doesn't collapse onto a self-similar behavior, because frankly, it's taking physically longer for this system to blend than that system, as it were. The turbulence forms other physics as well. Now, at these impeller speeds, we're not seeing a strong difference in bubble breakup, which means there's not a strong difference in KLA for these different systems. But we know that at higher impeller speeds, higher energy dissipation rates, more bubble breakup, we'll see higher KLAs. So turbulence spectra, energy dissipation rates associated with that turbulence, they drive a lot of our process engineering. Shear, etc., which is not necessarily related to EDR, but it is related to velocity gradients. It's again a function of the fluid viscosity. Now, to be sure, the strain rate as well is related to EDR. They're linked. EDR comes from strain, but strain is calculated directly from viscosity. So again, this idea of turbulence prevailing throughout our process engineering systems is not a big claim. And these principles are general. So here's just like a jet mixing, or rather I should say a nozzle. We don't have a jet mixing system. Here's just a nozzle. There's no classical recirculation. And if we squint real hard at this or our previously demonstrated systems, and we look at one little point, we'll see there are kind of periodic velocity fluctuations, and we can do things with this signal. We can take a velocity autocorrelation function if we wanted to, and an integral of that gives us some sort of a time scale associated with turbulence. We can take a Fourier transform of the autocorrelation function, and we do that particular set of operations. We recover something called like an energy density. Okay. And this is a useful way of characterizing how energy is distributed across the system and the relevant regimes of turbulence inside these types of flows. So again, whether it's a flow through a jet or an agitated vessel, and I'll speak to this point in the next slide, we can do these operators allow us to kind of recast this seemingly stochastic system into reciprocal space with a well-defined set of repeating characteristics. That is a a correlative integral scale, an inertial range governed by the Taylor scale, and a Kolmogorov dissipation range, I should say, where energy is being rapidly thermalized in this Kolmogorov dumpster. And we'll see here that for a given system, for a given turbulent system, these frequencies may be system dependent. But if we normalize by these intrinsic timescales, I'll speak to the next slide, all turbulent systems collapse onto the same distribution. So here's what that looks like. If we normalize by, say, the Kolmogorov length scale, which can be calculated from the Reynolds number or energy dissipation rate, viscosity, or whatnot, then we see that we get the same general energy distribution shape for each individual turbulent system. Some systems with more, and the integral of this, of course, will be the total energy in the system, the integral of energy over wave number. Now, of course, some systems have more energy, right? You might have a faster moving impeller or a faster moving jet, as it were. So you'll have a more total amount of energy inside that system, meaning you have more power, more energy being dissipated. But to be sure, the solution, especially in the phase space, is going to be self-similar, anchored to the Kolmogorov scale. Of a Kolmogorov scale describing the smallest eddies that exist inside the system, and this is linked just to Reynolds number or energy dissipation and viscosity. It doesn't care what the impeller type is. It doesn't care if it's a nozzle. It doesn't care what it is. All it knows is that the Kolmogorov length scale is informed by fluid mechanics, regardless of the topology driving the turbulence. And so if we anchor the Kolmogorov scale, all turbulence collapses onto the self-similar solution. Taylor scale as well is going to be related to Reynolds number. Again, it's an anchor that delineates the inertial subrange anisotropic eddy from the isotropic energy dissipating eddies between as they go through this viscous dissipation regime. Large eddies, again, with an integral length scale, characteristic of the impeller size, nozzle diameter, vessel tank size, etc., are these big, overreaching eddies that inform bulk transport, etc. They will be strongly correlated to system topology. They will be strongly correlated to impeller type. Because, of course, the topology of that oar, that flap, that nozzle, etc., the tank shape is driving the type of eddies that exist. But as soon as you get down to this inertial subrange, and as soon as you approach the Kolmogorov length scale, the integral scale is forgotten. And all we're remembering, as it were, and all we know, as it were, is the turbulence physics driving that cascade down to dissipation. And again, we can describe these length scales, these transition regions, using some of these characteristic length scales. I'll say integral, Taylor, Kolmogorov. Okay, and these speaking words I've been speaking about for the past few minutes. I'm going to use an agitated vessel and some pipes here today to illustrate this concept, but I think the point is sufficiently universal. How we model our system, how we run our simulation informs what physics we capture. The most foundational modeling approach we can use outside of molecular simulation is to use a direct numerical simulation or to directly solve Navier-Stokes. I'll touch on this point momentarily. This, in principle, demands a resolution sufficient to capture all the way down to the Kolmogorov length scale, okay? That requires a high resolution because these Kolmogorov length scales can be small, as it were. But foundationally, within the context of the simulation, everything is captured, right? We're resolving all of the eddies. We're resolving the smallest fluid structure that are containing some fragment of energy leaving the system. This is expensive, but it's complete, right? We're limited, it's limited in scope by Reynolds number, but it's exhaustive. As a step up from this, and we can do DNS simulation in M-Star practically, and I'll demonstrate that today, well through the transitional regime into low turbulence. At industrial scale, I'll speak to here momentarily. To bend a corner, make these things a bit more tractable, it's routine for us to go onto large eddy simulation. Large eddy, as the name suggests, captures only the large, that's the subjective name, eddies inside the system, bypassing some of the smaller scale structures that have length scale characterized by the Kolmogorov scale. The amount of spectrum we see, the amount of this distribution we see, will be informed by the lattice resolution. That is, a finer grid will eventually be recovered DNS simulation. A very coarse grid means maybe we're cutting off our nose in a region where we can't see a majority of the structure, as it were. So in large eddy, we want to be as close to DNS as possible while making it tractable from a simulation standpoint. But we certainly want to be within this Taylor scale. So we're poking into the dissipation range where that filter is designed to operate most effectively. RANs and unsteady RANs are kind of different animals. And honestly, like they're trying to model most of the physics that are not being captured explicitly, and they're painted in a lot of ways. Like they're kind of like, I don't know, philosophical. Like they capture everything but nothing. Like they're all length scales but no length scales. Like I don't know. At the end of the day, they're explicitly capturing the integral scale, and they're modeling, I should say, the totality of these subgrid effects. I strongly prefer resolving the physics explicitly. I strongly prefer seeing what's driving as much of the turbulent flow as possible. They're compelling, but if we can do this, if we can routinely run LES simulation, if we can routinely run DNS simulation, well, let's do it. I mean, RANs and URANs are cool, but they're kind of academically useful modeling paradigms in the light of these trivial LES DNS simulations, as we'll speak to today. And I'm going to be more aggressive about that point momentarily when I talk about some recent advances in literature where there's almost not a point. And I'll speak to that again with some papers just came out last week. So foundationally, we're not talking about just a watercolor picture of flow at some snapshot in time with some everything but nothing turbulence model. We're going to be resolving everything, and we're going to leave nothing behind, as it were, as we go to this DNS, and maybe leave some things behind as we go to LES. And so I'm not trying to like throw a bunch of shade on RANs. I'm saying like, what's the point when we can do this these days? And I'll speak to that more forcefully with some kind of compelling validation from the literature. Okay, so foundationally, this is what we're going to be going for today: a full resolution of all the structures, or maybe some subgrid modeling, and understand the transition between the two. I'm not talking about RANs. So what informs the idea of a DNS simulation? Well, when we're doing DNS simulations, we're obviously assuming that we have a fluid element, okay, such that we're ignoring the molecules driving the transport physics, okay? So we start with a discretized description of the fluid field, and we solve this equation. We're going to be solving these things using the Boltzmann transport equation, okay? Because that's a very efficient way to solve Navier-Stokes equations in 2024, going into 2025, especially on a GPU. And again, maybe I'll kind of bend this, I'll kind of recalibrate that point. We're not solving the Navier-Stokes equations using LBM. Nobody's solving the Navier-Stokes equations. If we were solving the Navier-Stokes equations, we'd be giving lectures at universities and receiving prizes. Everyone in this field is approximating solutions to Navier-Stokes equations. And the tool we use to approximate a solution, the Navier-Stokes equation, is the Boltzmann transport equation, as it were, solved in a way that recovers Navier-Stokes, again by linking viscosity, relaxation, and pressure to density, and the lattice velocity, speed of sound. And this is discussed in the literature for the past 30 years. When we're doing LES simulation, whether it's in the context of a finite volume approach or in the context of LBM, we typically use LES closure models that modify the local viscosity. These are called Smagorinsky-Lilly models. And the way they work is this. They say we are not going to capture all of the energy dissipation of the system. There will be some fraction of this spectrum that we're not seeing explicitly. But we know its net effect on the flow can be described via something called an eddy viscosity. Said again, we claim, or these subgrid models claim, that the net effect of this unresolved component on flow can be described by locally modifying the molecular viscosity of the fluid. And how do we modify that molecular viscosity? We modify it by looking at something called the local strain and something called the Smagorinsky coefficient. A lot of effort goes into figuring out what the Smagorinsky coefficient could be. It's generally settled to be around 0.1 by comparing LES DNS simulations. Some people argue for 0.08, some people argue for 0.2, but foundationally, there isn't a huge knob tuning going on there. And in M-Star, we'll never really change it. But foundationally, this is the crux and claim of LES, that we can bypass some of this subgrid scale here and really soften the blow associated with DNS resolution and bend a corner with running DNS simulation if we're willing to assume that some of these smallest eddies, those close to Kolmogorov scale, can be reasonably represented as having a net effect on the molecular viscosity, which isn't a bad assumption, and it's discussed at length in Pope, but to be sure, you've got to make sure you have a set of eddies that satisfy that close to Kolmogorov length scale condition. So again, within the context of LBM, just to kind of illustrate this here, this is time accurate and three-dimensional. Like we are not looking at a mean snapshot of the flow field and then superimposing or injecting energy dissipation rate or vecting K and epsilon, as it were. We're actually tracking the time evolution of the velocity. We're calculating the local strain. We're calculating the local energy dissipation rate and using that to calculate the total energy dissipation across the fluid volume. So we can calculate the time average. We're not using that for our calculation. We're using the time-varying flow field, as it were, to calculate time-varying EDR strains, etc. We can then use that to inform time-dependent physics, for example, mixing processes. Again, we're solving all these physics on the same lattice at the same time scale. So the key point is that it's easy for us to interrogate these turbulent processes at high resolutions because we're starting with a high-resolution, fully transient modeling approach out the gate. It does have molecular origins, of course. We're not using molecular physics to solve LBM. We're using the Boltzmann transport equation. But again, as we've talked about in past lectures, and we can speak to offline if people want to know more about it, Boltzmann comes directly from molecular kinetic theory. Like that's its origin story. It comes from molecular transport physics to arrive at this phase-space distribution as a way to attack Navier-Stokes. Navier-Stokes are typically derived from finite volume-based approaches. You can recover them using molecular physics. But that was my PhD, was recovering Navier-Stokes from MD simulation, actually. Okay, so for today, I'm talking about DNS and LES industrial scale. So I mean industrial scale. Like when we talk about LES DNS simulations, especially DNS in the literature, it's often like, oh, I did like a cubic centimeter, or oh, I did like some flow over a pinhead. Like I want to do a real vessel. Like I want to do DNS at like hundreds of liters, as it were, and LES routinely at thousands of liters. And so when I'm talking about hundreds of liters of fluid, or if not thousands of liters, if we're tolerant LES. I want to do DNS hundreds of liters. I need to be able to run these things like overnight. A industrial scale DNS simulation that takes 2 months to run has no industrial utility. I need faster runtime. Furthermore, I need these things to be kind of commercially practical. I need to be able to run on hardware that costs tens of thousands of dollars, not millions of dollars. So I'm looking for good, fast, and cheap. I'm looking for all three. See if we can get it here with some better algorithms. I want good code that can run hundreds of thousands of liters. I want things to run fast, overnight or within a workday. And I want it to be cheap to run on desktop hardware or $10,000, $20,000 hardware, not $1 million supercomputer. So, okay, if we're going to set these up, let's talk about kind of where we're going to model this. I'm going to try to model a system to make it easy on me as possible. I'm going to stick with Reynolds numbers at like no lower than like 10,000, 9,000, because an agitated vessel, pipe flow system, etc. Like below that, I started to get into transitional laminar regimes. And so that's kind of, I don't want to run something like 1,000, Reynolds number 1,000, and claim it's turbulent. I want to be hand to heaven turbulent. So I'm going to be running around 10,000, as it were. That would give me compelling Reynolds numbers and turbulent systems for both agitated systems and the pipes I'll speak to momentarily. When I need to be able to run for an agitated vessel, dozens of impeller turns, right? If I'm really trying to predict EDR. I can't just do like one turn of an impeller and claim that I've done DNS. Like I need to run dozens, hundreds of impeller turns, as it were, in this higher Reynolds numbers regime to really convince myself that I'm doing a proper simulation and to DNS at boot. And we expect self-similarity between the turbulent spectra as we get to these turbulent systems. Because if I get below here, like the distribution changes. It won't even be a turbulent spectrum anymore. And so I want to be at a point where the distribution is self-similar. I mean, length scales can be honestly compared between the different systems. Let's start with the agitated vessel, as it were. So here I've got, it's fair. It's 30 centimeters in diameter. It's pilot scale, maybe pilot or large bench. It's 10 centimeter impeller. It's coming. It's what this is going to be. This is going to be, a couple hundred liters of fluid. Okay. I've got water in there spinning at 60 RPM. I'm going to have just a 45-degree pitch blade. Impeller is baffled, of course. This is a Reynolds number of about 10,000. Okay. My Taylor scale is about a centimeter. That is like, and again, Reynolds number is 200 micrometers, just to kind of contextualize these things. Okay. I'm using equals, but it's a soft equals. Okay. When I say my Kolmogorov scale is 300 micrometers, it's about that. Okay. Like there are squigglies in their derivation of Kolmogorov and Taylor. So I say my Taylor is 1 centimeter. I'm like, okay, do an order of magnitude. Maybe it's 5 millimeters. Maybe it's 1.5 centimeters. Do an order of magnitude, it's a centimeter. which would correspond to, about 300 points across this vessel. 300 lattice points, I should say. No, 10 lattice points, 30 lattice points, which is too coarse, so we know that's going to be lower than that. But either way, that's an easy resolution to achieve. 300 micrometers, that's harder, right? That's going to be approaching something like 1,000 points across this vessel, as it were, somewhere around there. But to be sure, these are the intrinsic time length scales associated with a flow of this Reynolds number. And again, because I'm looking at kind of that bottom tail of the distribution, whether it's a pitch blade, whether it's Russian, whether it's pipe flow, as I'll show momentarily, these length scales, as long as they're anchored to the Reynolds number and the device length scale, don't care how the turbulence is being produced. So let's do our first simulation somewhere between Taylor and Kolmogorov. I'll set the resolution to 1 millimeter, which is kind of between those length scales. And here's just a canonical, predictable, unremarkable M-Star simulation, okay? Watching the flow evolve, nothing unique here. I've got LES turned on, of course, as I must, because I'm nowhere near DNS. But there are some things to note. This thing has about 27 million grid points, right? I'm running at about, 2 million time steps, as it were. In order to run this kind of like 60-second simulation, that requires about 5 trillion lattice updates. That is a lattice points times time steps, and it takes about an hour on 1V100. It takes far less on A100, about half that. But to be sure, okay, we're in play. Like, just looking at these numbers, I'm running a lab scale system for 60 seconds, okay, like in under an hour. So like, okay, this is in play, this idea of kind of doing these LES simulations. I'm not at DNS yet, but my first stake in the ground is, okay, yeah, I'm shooting my first shot, and like, I'm kind of in the right ballpark. Now, let's consider the first law here. We know from the simulation, like, what the torque on this impeller must be. That comes out of the code. We know what the torque on the impeller must be. And we can calculate that torque, that times the angular velocity, gives us the power. We can calculate how much shaft power is going into this thing in order to spin the impeller at that 60 RPM speed. We know from experiment that the power number of this pitchman impeller is like 1.3. Somewhere 1.3, we'll say that. Maybe it's 1.4 for this configuration. Maybe it's 1.25. At the end of the day, it's going to be 1.3, we'll say that. So we know what the kind of expected power should be for this particular configuration. And voila, lo and behold, we see that the code can correctly predict the amount of power that's going into the system by calculating the torque on that fluid. The torque on the impeller as it spins through the fluid. Likewise, we can go through this fluid domain and calculate the local energy dissipation rate. So that again, every single voxel, I can compute what the energy dissipation rate is. Energy dissipation rate is viscosity times the strain rate tensor, the square of the strain rate tensor. Double dot product of the strain rate tensor. They're all the same thing. But to ensure every point, I can calculate EDR. Okay. So I know what the EDR is here. And this is log scale because EDR varies so greatly throughout a typical vessel like this. We have orders of magnitude variation, energy dissipation in a turbulent vessel, which isn't surprising. We have very low near the top of the tank, and it gets rocked in the trailing vortex. But to be sure, I can integrate the energy dissipation rates across all voxels. I can add every point up to get the total EDR, energy dissipation rate, inside the system. This is wholly independent from that torque calculation I spoke about earlier in terms of the green plot. And this is a routine in M-Star. When I add up all of these energy dissipation rates across the entire vessel and I integrate that over the entire volume, I get the red line here. Okay. And I'm seeing here the energy is conserved. This was not a DNS, this is LES simulation. It's not capturing the full spectrum. What it is telling us is that the LES filter and that Lillie-Smagorinsky theory, well, gee whiz, it works. It works. Like, here we are. These are two independent predictions on power dissipation that are converged as the first law expects them to be. And their steady state behavior is agreeing with measured power number data. That's pretty compelling. Now, I've asked the question before, and I'm not going to put you on the spot, but like, people might say, but wait, why does power in exceed power dissipation for the first like 5 seconds? It should, because the fluid is accelerating, right? The kinetic energy inside the fluid is accumulating, and after maybe 20 seconds or so, we're finally at a balance where I've topped off the fluid with all the energy it needs in order to maintain some sort of set kinetic energy, which is constant throughout the remainder of the process. Said again, I'm pouring energy into the system, faster is being dissipated, the net effective energy is accumulated, energy is kinetic energy in the system, and eventually reaches steady state where the rate at which I'm pouring energy in for the impeller is the rate at which it's being dissipated, is the rate at which it's being heated up. Kind of neat. But it's kind of cool here to see the LES filter work, even when we're running in this kind of intermediate between Kolmogorov and Taylor with the LES filter on. Now, we know, though, with the LES filter, how much we're seeing and how much we're missing. So again, we can decompose this total energy dissipation rate into two things, the resolved and the unresolved. We can see how hard the subgrid filter is working, how much energy it's mopping up that was missed by the grid explicitly. So again, our grid resolution here is not sufficient to see all the way down to Kolmogorov, which means there is some energy dissipation, some component of that spectrum that is not being captured by the simulation, that is instead being captured by the Lilly-Smagrinsky model. Well, we know how much it is. So we know there's a resolved component and an unresolved component. Now, for our engineering processes, we're overwhelmingly interested in the total, right? We want the total EDR to inform bubble breakup, or the total EDR to inform reaction kinetics, or the total EDR to potentially inform dissolution rates, as it were. But to be sure, we can peel back the veil a bit and see, oh, there's some that's resolved and there's some that's unresolved. And the code spits it out automatically, so you can see it. And in fact, we can even be more granular here and see where the LES filter is doing its work, okay? So this is the molecular viscosity divided by the molecular viscosity plus the eddy viscosity, okay? Where this is 1, it means that this term is very small compared to the molecular viscosity. It's insignificant. In a majority of the vessel, the effect of the LES filter, that is the adjustment to the molecular viscosity due to the unresolved flow physics, is pretty negligible. In the immediate vicinity of the impeller and right inside the trailing vortex, there we see the effect of the LES filter meaningful. That's not to say that the energy dissipation rate there is wrong. It's right because we integrate to the correct value, but that's where we're kind of turning those gears of the subgrid model. That's where it's coming into play. Like that's where the subgrid model has to do its thing, because that's where a lot of these small grid eddies live, as it were, that aren't being captured explicitly by just Navier-Stokes, that is said to be topped off by the subgrid model. It's kind of cool to see that net effect, both in terms of the total energy dissipation as well as the local effect of the algorithm. Again, I'm kind of peeling back the curtain here. For 99% of our processes, the total EDR is all that matters. The fact that the code gets that right is all that matters. Here, kind of peeling back and exploring some of the nuances of resolved versus unresolved is interesting for today's discussion, but not really immediately relevant to kind of a process simulation. But it's interesting for today because watch this. So what would we expect would happen as I increase my resolution? Well, as I increase my resolution, I'm going to be seeing more and more and more of that turbulent energy explicitly, right? I'm going to be relying less and less on this filter. Like I should be seeing more. So again, this delta X, as my resolution gets finer and finer and finer, that should get closer to 0, right? And the flow field here, the flow field doesn't change. You're not going to see strong changes in strain. But if this delta, and I'll speak to that momentarily, the selective power, but as this delta X gets smaller and smaller and smaller, like this is going to go to unity everywhere, implying I'm kind of approaching and recovering DNS. Let's watch this. So here is me cranking up the resolution of the simulation, going from 1 millimeter, 0.5, 0.4, 0.3. And this is the resolved component of the energy dissipation. What am I seeing here? The total shaft power isn't changing. I'll kind of talk about this next in the live demo. The total shaft power isn't changing. The flow field is changing. The power number doesn't change as I change resolution and when I'm in a fully converged regime, right? I'm not putting more power into the system as my resolution goes up. But what's happening here is I'm able to see more of that energy dissipation explicitly without the need for the LES. And when I get down to 0.3 millimeters, look at this. My total energy dissipation, shown here in blue, is riding right on top of my experimental and my shaft power. And what's unique about that 0.3 millimeter length scale? Why did they get their 0.3? That was the Kolmogorov scale, right? That was the Kolmogorov scale. I spoke to it and I was like, these are squiggly lines. But at the end of the day, 0.3 is a pretty good estimate. But that's why I converged there. Like, why did we get to the point where we saw all energy dissipation around a resolution of 0.3, because at that point, we completed the spectrum. Below here, why did we not resolve everything explicitly with a low resolution? Because we didn't resolve the full spectrum. That doesn't mean we can't reliably predict energy dissipation rate. We know how much is subgrid. We report that inside the code, but it's cool to see as I crank down on resolution, as this goes to 0. Let me go back. Sorry to be jumping around here. But and as this resolution goes up, this red bar goes up, 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 up. As I drop my resolution, eventually all is resolved, as we would expect the Lillie-Smagridsky model to do. I'll speak to this in more detail. I have a, I'm going to see if this works. Sometimes this can be a bit, okay, let's see if this takes. Okay, let me jump back and forth just so I can show what folks going on. I want to talk about this in more detail to illustrate the idea of resolution. I'll stick to this slide first and we'll jump back to my machine. Here was me running that system at 3 different Reynolds numbers with a constant resolution of 2.5 millimeters, okay? At these 3 different resolutions, I have 3 different Taylor and 3 different Kolmogorov length scales. The Taylor scale is larger than the Kolmogorov length scale. At a Reynolds number of 9,000, I've got a Kolmogorov length scale of about 0.5 millimeters, as it were, and a Taylor of about 20. If I run at 2.5 millimeters, I get a power number of like 1.3, 1.4 for this particular pitch split impeller. Makes sense. If I go to a higher Reynolds number, my Taylor and Kolmogorov change necessarily. There's fire fluid structures inside the system. I keep my resolution the same. My power number, lo and behold, is the same. That is said again, as I change resolution, the amount of power I'm putting into this impeller isn't changing, right? Resolution isn't changing the amount of torque on this impeller. Resolution is only changing, I should say, how much energy I'm seeing explicitly. Likewise, as I go from Reynolds number of 9,000 to 27,000, as it were, I'm in the fully turbulent regime. My power number isn't going to change as I go from 9,000, 27,000, 83,000, etc. The power number is the power number is the power number. It's not changing, despite the fact that the resolution is changing beneath my feet. So the first point that we're seeing here is that for me to reliably predict power, shaft power, etc., I don't need to be doing DNS, right? I can be well above the Kolmogorov length scale and still be reliably predicting shaft powers. In fact, I think in as much as I'm below the Taylor scale, I'm probably going to reliably predict shaft powers. But importantly, as I shift my Reynolds number here, my power number does not change. Yes, total power changes, of course. I'll speak to the next slide, but power number does not. But beneath the feet of the simulation, Kolmogorov length scale R as we go to these higher resolutions. Now let's look at energy dissipation rate. So here again, same lineup, 9,000, 27, 83,000 as it were. I got power on the left axis. To be careful, these scales are shifting because they're so different. Said again, as I go from, and these are all achieved by changing the impeller speed. This is impeller speed of 20 RPM. This is 180. We know that power input changes as n to the 3rd power. And so I couldn't put these on the same scale. But that's not the point I'm trying to make here. The point is this. At each of these Reynolds numbers, for a fixed resolution, I'm still, hand over heart, able to capture what the what the power number will be, what the shaft power will be, and I can correctly index all the EDR. Said again, I can reliably predict EDR, and I can serve the first. I can satisfy the first law at all of these Reynolds number. Kind of neat, as it were. What's interesting here is the resolved component, as I go to higher Reynolds numbers, becomes an increasingly smaller fraction of what I'm actually seeing inside the simulation. So then again, 2.5 millimeters at a resolution of 9,000, I'm explicitly seeing about half the power. Not bad, which is what I showed before at that resolution on the previous slide. But if I go to higher Reynolds numbers, keeping the resolution fixed, it does not dramatically poison the quality of the power of the energy dissipation rates and the blend times, as it were. But what it does mean is that that resolution is seeing less of the energy spectrum explicitly. Said again, I'll go back to this slide. Sorry to be jumping around, but this is a great slide. Said again, my resolution is now represents a value further to the left on this scale. My bar here is going to the left relative to the Kolmogorov length scale. That is, actually, I should say it another way. The bar here is, my point here is constant because my resolution is constant. That informs how much the spectrum is seen explicitly. But the Kolmogorov length scale is smaller, meaning this tail relatively is getting to the right, which means there's more and more and more of this energy, this portion energy, that I'm not seeing explicitly. And so here I'm shifting not the resolution, but the Reynolds number under the feet of the LES filter and kind of watching it respond. Sorry to be jumping around, but it's kind of cool. And so again, from a macroscopic standpoint, from a power number, total EDR, local EDR, it's all good. What this is telling me that at some of these higher powered voxels near the impeller or whatnot, the subgrid model is doing its job and doing it well in the sense that it's correctly capturing the total EDR, as it were, despite the fact only explicitly resolving, in this case, less than 10%, right? Less than 10%. And again, it's kind of a neat way to kind of interrogate this from the other direction. Here I'm keeping resolution fixed and changing Reynolds number and seeing, aha, I'm still conserving first law, and my total energy dissipation rates are correct, as it were. But as I change the sand beneath the feet of the simulation, feet being the resolution here, I'm actually kind of moving the magnifying glass as to where how much the energy I'm resolving explicitly. Said again, if I want to do DNS at this resolution, I might have to triple my resolution. If I want to do DNS at this resolution, if I want to do DNS at this Reynolds number, I might have to double or triple my resolution. I'm about halfway there. If I want to do DNS at this Reynolds number, I'm not getting there. I'd have to have like a 50 times higher resolution. I'd really need to gobble up a lot of missing energy here. So this tells me how close I am. In this place, it's hopeless. You got to use LES. In this place, in play, as it were, and be able to see kind of the balloon squeeze between the two regimes while kind of nicely passing the ball is really compelling. Same thing works for pipes. I've been talking about actually systems, but hey, pipes are turbulent too. And I made this claim. That the turbulent spectra shouldn't care how it got there, right? If we have a free turbulent flow, yes, if it's narrowly wall bonded, there might be issues. But if we have a sufficiently large diameter, as it were, that the length scales of the turbulence are small compared to the integral scale, where there's an agitator, whether it's a pipe flow downstream of a turbulence trip, as it were, foundationally, we're going to have the same general Kolmogorov spectra, the same energy spectra, down as you get to the integral and Kolmogorov length scales. And so these physics should work. And they do. I spoke about this last time during our heat transfer seminar and talked about how very high resolution M-Star simulations recover this near wall behavior. When I say very high, this is 16 billion grid points on like a 64 GPU DGX system from NVIDIA. But so that's very high resolution. But to be sure, it's kind of like there as like the goalpost. There is like the standard. Again, now that we have this in the bank, we can compare against it and see how LES filters behave as we go to coarser resolutions, where we may not want to run 16 billion grid point simulations. We can compare results to them. But to be sure, if we turn on the gas, yes, we can do DNS simulation in pipes as well. And that often requires probing down into the wall region, as it were, and appropriately modeling that buffer layer and poking into the sublayer as well as necessary. Although it may not be necessary, as I'll speak to momentarily with some ILAS simulations. But to be sure, I was concerned about my machine going down. Not that my machines go down all the time, but you never want to have like a machine go down and be like, oh, well, I'm sorry, I can't show the demo. All the data's here in M-Star. I can send the files one. It's super easy file. Just tag. I then did one more though. Here I just put like this static mixing system. Okay, I put a static mixer in here and I just had it like crank. I just had it run and I just had it flow through. Let me just go over to this guy real fast. I'll show you what this looks like. I'm just looking at it, having a day. Kind of there's a snapshot of the velocity field. Let me go over to my 2D slices, and you'll see it's an unremarkable pipe flow simulation, but nonetheless it's turbulent, right? Nonetheless it's got dissipation scales. Nonetheless, it's got a Kolmogorov scale, a Taylor scale, etc. But as I watch this guy go, it's just just turbulent flow, just having a good time. It's just kind of booting up here for the first second. And I get some turbulence downstream. This looking at one cut plane through it. After 1 second, I had my flow, my ramp finished, and I'll see my turbulence downstream here as I have this low viscosity fluid go through this kind of turbulence-inducing elements, and I'll call them that to avoid any ambiguity. But to be sure, there's just my flow there. As I go through this guy, I can see, some characteristic data here. I'll also look at my inlet. I can see that my velocity ramped up the inlet velocity, reaching steady state flow conditions after about a second. And my flow rate here was, corresponding to, what do we got here? Yeah, about 0.0077 meters cubed per second, about 7.7 liters per second. The pressure of the inlet, as this guy ramps up, he settles in to around, 68, 6,500, I'm sorry, gauge pressure, 106.5 kilopascals or whatnot. That's the pressure the inlet ramps up to in order to drive the flow through this system at this flow rate with this viscosity, given the topology of the system. The outlet, similar story. The outlet kind of responds to the increase in flow rate, then snaps on to the exit velocity. The exit pressure was maintained at 1 atm. So if I go to it was just pressure boundary condition and inlet boundary condition with a ramp of 1 second. So if I go to this guy back over here, so annoying to me sometimes to use RDP. But to be sure, my flow rate here, I'm conserving mass. That's like necessary. My pressure was maintained. But foundationally, I can look at these pressures as it were. I look at thermodynamics too. I can see, for example, here is my total power dissipation. Here is my result. This isn't DNS, but it's kind of close. And I'll speak to that momentarily. So like, okay, but are we just going to trust it? No, we're going to like look at it more aggressively. So here's that. Here are pictures of that. Here's the inlet. Here's the outlet. I know that my Reynolds number was 5,000. So I'm turbulent. I'm above 2,300. This is a full, and I've got little trips in there, those static mixers. This is a turbulent flow. It's not just if I was looking at a Moody chart, I'd be turbulent. My Taylor scale is on the order of 5.4 millimeters. My Kolmogorov scale is 0.16. I'm between the two. I'm running about 0.5. So I'm not going to see everything, but I'm not too far away from DNS, as evidenced by this guy here. I know just from like conservation of energy. Well, I'm conserving mass. That's a necessity. And I have some pressure difference here. Like there's a pressure drop between the inlet and the outlet. Like I know, like fluid mechanics 101, like fluid mechanics 101. It's on my desk too, because I'm always reading it. Because I'm always trying to remember what I learned many years ago. But to be sure, fluid mechanics 101. We know that the power going into the system, the amount of power it takes to power that flow going through that system is going to be delta P, the pressure times the flow rate, right? That's how much power it takes to push fluid through a continuous flow system. Makes sense. Pressure is energy density. Pressure is units of Pascal per meter cube. I'm sorry, joule per meter cube. Flow rate is meters cubed per second. So obviously you have a flow rate times energy density gives you a power, a energy flow in terms of joules per second. I'm sorry, yeah, joules per second. So we recover, if we look at this pressure drop, look at the flow rate, we get about 42 watts. And what do we get when we integrate the power dissipation? And this one I got about 40, but I'll take it. Like, again, this is totally independent. Like I'm integrating, and I was 200 resolves to the wall, which I'm a little bit off. I'll speak to that in a minute. But to be sure, it's like not bad. Like I'm taking the system here. I'm integrating power dissipation over the entire system. Let me go back over to this guy. I'll show it here again. So here's my 3D representation. I can calculate the energy dissipation rate at every point, as it were. I can integrate that energy dissipation over the entire system. I can sum it up, and I can check it against the pressure drop times the flow rate and see that they're within like 4%. Like that's a pretty cool application of both energy conservation, the first law, and the LES filter. And you can actually see why. Like we weren't super far off from DNS. Well, not surprisingly, because in this particular system, we weren't too far off from Kolmogorov's length scale, right? I mean, again, is Kolmogorov 0.16? Should it be 0.3? Should it be 0.018? I don't know. At the end of the day, it's around maybe 0.2 millimeters. Our resolution 0.5 is not surprising that we got most of it. As it were. It's not surprising we got most of it. And it's cool to see that confirmation go through. Let me just jump over to this guy and see. There's the velocity field in 3D. Kind of having a good time there, just having a day. And let's go to EDR. I've got energy dissipation rate. This is going to be very high inside the trailing vortices here. Let's see if I can but it's going to be kind of high inside those little kind of, not trailing vortices, inside those structures there. Let me see if I can scale this down a bit so I can see more action in this live demo. Fiddlesticks. It wasn't going to work for me because I put too many zeros in there. See if this works. Okay, getting closer. At the end of the day, there's kind of the EDR map of the system as it moves through. But it's very compelling to see this kind of Kolmogorov, Taylor, resolution bounce, see energy conserved. Again, I'll take my 4%. I'll take it. To see kind of why it's there, why I'm capturing most of explicit as a function of DX. It's kind of neat to see. And comments on speed. Do we have any authors from this paper here? Is Sarush here? I don't know if he's here or not. Okay, that's fine. Let's talk about speed. And this is this is why I was kind of like cagey on RANs. Because like I'm like, well, what's the point at this point? And I got a more compelling slide. I don't know if Sarush is here. He was author on that paper. But like, okay, I'm gonna skip this slide and just say like, look out. Oh, Sarush is here. Oh, there's it. Great, great. I'm gonna speak to your paper. Maybe you should get a t-shirt. But it's maybe I can have the factory cough another one out. But I'm just gonna say this is like a few years ago, people knew this was coming. Okay, people knew that like practical industrial scale LES was here. Okay, and they were like, it's probably gonna be LBM that does it. And I was like, hi, professor, my name's John Thomas. We're doing it. It's 5 years ago. I meant that. I'm like, hey, good news. But either way, and like, here's why. Like these machines, these are like, beefy desktop resources when you get like 2 or 4 GPUs in it. But to be sure, like you can comfortably host billions of grid points on a modern multi-GPU node, as it were. And again, look out what's coming around the corner. These haven't been released yet, but even these 5090s, they have 4 times as many CUDA cores on them. They're going to run 4 times faster than the current V100s, and they're gaming GPUs. Like there is a punctuation going on here in terms of the GPU hardware that is going to make DNS and LES. LES industrial scale is already done. We're doing that now in wastewater treatment facilities. But watch out for DNS crawling up and up and up and up that Reynolds Reynolds length scale, as it were, eliminating the need for subgrid models altogether, which is pretty compelling. And here's Sarush's paper. Great paper, by the way. Sarush, I'm going to just speak to a couple key points here. And contact, I shouldn't use your name in vain, but Sarush is the author. Are you the contact author? I think you are. I can't see her. Either way. But so I'll kind of talk to Sarush. You got questions. This is a great paper because it was an apples-to-apples comparison between LBM and finite volume-based approaches and what are the gives and gets. And that's a real kind of important, it said the quiet part out loud, is that, hey, we're all solving the same physics here. We're all solving the governing equations. We're all attempting to solve Navier-Stokes. M-Star attacks it using LBM. I think you're using star CCM, which is a very widely used tool, kind of attacks it using finite difference and finite volume, as like OpenFOAM and other tools do. And Sarush, my understanding was this, is that both approaches, both attacks can give you very similar results, which is great because we're both attacking the same governing equation, but the way we attack it and the physics we get out differ tremendously. Said again, like when we're doing LBM on GPUs, we're immediately doing LES, and we're running these things very quickly across fine resolutions. When we're using finite volume-based approaches, we're using coarser grids and typically using like a URANs with a K epsilon. And here's kind of the punchline. And again, Sarush, you can speak more to this than I can. Maybe you should give the next seminar. But to be sure, like here's this point. Like in terms of efficiency, a significant difference is observed between the two methods. Like in the M-Star method, leveraging GPUs and the smaller time step, like it takes about 4 hours to run the 30-second simulation. Using finite volume on URANs, nonetheless, which isn't even giving us that small pyramid structure, it's 41 days. Like it's not even close. And here's kind of the point. And we're not claiming like, oh, well, here's a new paradigm for solving Navier-Stokes. No, not at all. Well, the theory in M-Star is 50 years old. Lily Smagorinsky is from the 60s, I think, maybe 70s. I need to double check. But all these LBM algorithms from the 90s. What's really bringing this thing some punch is the fact that when you put it on these GPU architectures, you get better physics. You're getting 10 times the resolution at a fraction of the time step, which is important for reaction, suspension, KLA, mass transfer. This isn't a moral victory. There is utility, especially when having a multi-physics system, being able to split a smaller time step. The smaller time step, a 6x resolution running 250 times faster. Like that's a real punchline as to why, like the idea of, well, I've got this creaky RANs, like eventually the gig is up. And it's like, it becomes kind of I don't know, it's like eventually someone's boss is going to find out and be like, wait, why aren't we doing this kind of these more emerging technologies with kind of LES and DNS? A quick point here at the end, just as an aside, there is a third way within the context of these turbulence models called ILES. This is an M-Star. I run it all the time. I love LES. Here's a model of me using LES right now for this very complex rheology. If I go to this guy, look at ILES right there inside this model. This is like a complex Herschel bulkly off-gassy model. But at the end of the day, it's got ILES because I got very strong variation of viscosity. ILES stands for implicit large eddy simulation. ILES does not modify the local viscosity. It does not sprinkle in any eddy viscosity, which means it can capture the molecular viscosity explicitly. These higher order methods do a very good job of resolving things like the turbulence catastrophe as drag over a sphere, or the pressure drop over a sphere in crossflow, as it were. What's neat about this is because they're not adulterating the viscosity a bit, they can capture these very sensitive, these physics that are very sensitive to Reynolds number. So again, if you're squeezing around with viscosity and trying to observe a function that is closely related to Reynolds number, the ground might be moving underneath your feet. It might be hard to pin that down. You need to use an approach that doesn't monkey around with viscosity. Same thing with transitional flows. If you're doing like some system with a strong variation in viscosity due to, say, some non-Newtonian effects, this ILES is awesome because we're not sprinkling viscosity into the code and therefore changing the rheology in a detrimental way. Like when you have systems where you got to get viscosity right, getting some sort of, whether it be some sort of Reynolds number dependent transition criteria or some transitional flow, these implicit approaches are awesome because they don't adulterate viscosity, as it were, and they're higher order. So just a kind of thought that, hey, these guys are here too, and they have utility. It's not just DNS and LES. ILES, implicit large eddy, it's got a very strong utility that we can speak to on a case-by-case basis. They do some great validation work on me. This is not my work. This was published years ago, but I just wanted to mention this third rail. Keep apprised of it. Guys, I want to get to the giveaway. We move way beyond RANds. Time accurate, LES and DNS are practical for the LES. Sorry about that. It's interesting to see grid space being a magnifying glass for the simulation. These models for LES are shear thickening. ILS can be attractive. Boy, I'm running out of time. I see like the stagehand waving me off. But yeah, importantly, it's kind of an attractive approach to doing industrial scale systems.